Cool, thanks. Welcome to our presentation entitled Laying Groundwork for PDNA, Next Generation Wastewater Treatment in New Zealand. I'm Louis Ortenzio and this is Song Lee. We're both wastewater engineers at Lutra. Before we get started, just wanted to give a few acknowledgements and thanks. We want to thank Palmerston North City Council wastewater team for helping us run our pilot for several months at their site. We want to thank Annamox, Caldenus, and Veolia for providing some support on a full-scale application coming up in 2026. And then last but not least, we want to thank South Waikato District Council for being open-minded and ambitious enough to pursue PDNA with us at the Tokoroa Wastewater Treatment Plant. So to cover our agenda for the presentation, we're going to talk about biological nutrient removal as a whole, talk quickly about Annamox and compare the PNA and PDNA processes, global PDNA activity and its potential relevance to New Zealand, then jump to summarizing a pilot study we did at Palmerston North City Council where we investigated a facet of PDNA, and discuss a full-scale application where we're going to test PDNA in 2026. So there's been a lot of development in nitrogen removal pathways in the last 20 years. Historically, it was always a two-step process. Shown here is conventional nitrification and denitrification, where ammonia is converted to nitrite and then to nitrate. And that's nitrification, and then nitrate to nitrite and nitrite to nitrogen gas in a process called denitrification. So in the early 2000s, there was a lot of development with a bacteria called Annamox and exploring a process called PNA, which stands for Partial Denitrification Annamox, which is shown in the middle, where ammonia is converted to nitrite, and then ammonia and nitrite are converted to nitrogen gas and a small amount of nitrate per the Annamox process. Then in the early 2010s, another process using Annamox started to be explored called PDNA, which is partial denitrification Annamox. So in that case, you already have nitrified your ammonia into nitrate. So you take nitrate and you dose a small amount of carbon to short circuit or basically disrupt denitrification to produce nitrite. And you take that nitrite with residual ammonia with the Annamox process and you produce nitrogen gas. And again, a small amount of nitrate. So there's also simultaneous night-denite. We don't really cover that here. There's a lot of development in simultaneous night-denite or SNDN. It's a really sexy thing right now, but we don't have anything to offer on that. So let's talk a little bit more about PNA and PDNA, but first we want to introduce Annamox properly. So first, what is Annamox? It's an abbreviation for anaerobic ammonia oxidation and utilizes a slow-growing bacteria that's distinctively red, and it's autotrophic, so it's an autotrophic bacteria. It's naturally occurring and ubiquitous in water and wastewater, and what Annamox bacteria does is it takes, and I've already mentioned it, but it takes ammonia and nitrite, reacts that to nitrogen gas, and produces about 10% of nitrate from the ammonia that's being removed. So Annamox technologies have been adopted globally as an intensification process to provide shortcut nitrogen removal rather than having to perform nitrification, denitrification conventionally. So the primary challenge for adopting Annamox in New Zealand is establishing an Annamox bacteria population. So starting from scratch, it can take about a year or more to develop a seed population of Annamox. And New Zealand biosecurity makes it so we can't bypass that hurdle. Several countries are able to import seed bacteria from other countries and bypass this barrier, but because of New Zealand biosecurity, we can't do that here. So WaterCare successfully grew a bench scale population in 2018, and then they were able to transition that to pilot scale, but that's where that ended. And so sadly, we don't have any full-scale installations of Annamox technologies in New Zealand, and very few in Australia at this point in time. So that's a barrier. I'm just going to set that aside for now. When it comes to implementing Annamox technologies, one of the reactants is nitrite, which isn't particularly stable in wastewater treatment environments. So the Annamox process needs to be coupled with another biological process to produce the required nitrite. And that flows into our next two slides where we discuss PNA and PDNA, which are treatment processes based on biological reactions to produce that nitrite, and then couple it with Annamox to do the ammonia nitrite to nitrogen gas. So PNA, which we already talked about, partial nitridation annamox, is the most common annamox process globally and is typically used to treat centrate from anaerobic digestion. In PNA, ammonia is converted to nitrite in partial nitridation. This is done by creating a reactor environment which promotes ammonia oxidizing bacteria, which are AOBs, to outcompete nitrite oxidizing bacteria, which are NOBs. So you use things like pH, residual ammonia concentrations, DO, and temperature, and manage them to promote AOB growth over NOB growth. In normal wastewater treatment, NOBs will outcompete AOBs, which is why you rarely see appreciable nitrite concentrations. You might see like a 0.5 milligram per liter, maybe up to 1 milligram per liter, but rarely do you ever see that high. Because typically the AOB process is the rate limiting step in nitrification. So okay, we're past that. After you have nitrite residual from AOB activity, the annamox process takes place. So again, ammonia and nitrite are converted to nitrogen gas and about 10% of nitrate. PNA requires a small amount of aeration and alkalinity because of the partial nitridation aspect of this, but it's a lot less and you save greatly compared to conventional nite-denite. So something to note about PNA is that the reactor environment is a heavily engineered environment and can be challenging to create and maintain without this seed bacteria. So you typically have to trick it into steady state to create all these conditions which promote AOBs to outcompete NOBs. But once you get to that steady state, it's a relatively stable process, which is why there are hundreds of PNA installations and references globally. So PDNA is a relatively new mainstream process and is typically used for nitrogen polishing. In PDNA, most ammonia has already been nitrified, so we start with nitrate as a reactant and an ammonia residual from upstream processes. Partial denitrification is executed by dosing an insufficient amount of carbon, which disrupts the full denitrification process and produces a nitrite residual. So the partial denitrification is performed by ordinary heterotrophic organisms, or OHOs, and the nitrite and residual ammonia are then treated via the annamox process, which I've mentioned 5 or 6 times already. So just quickly, some very high-level benefits of PDNA. You remove nitrate as you should in denitrification, but you do it with less carbon consumption. Additionally, you also get more ammonia removal in PDNA than you do in conventional denitrification. It's worth noting that there's always a bit of ammonia removal in denitrification because of bioassimilation and cellular synthesis, but in PDNA you get significantly more ammonia removal. Another important note is that the environment for PDNA, so the reactor environment, is far less engineered than PNA and is easier to create and maintain, and so much so that recently in the last couple years, there have been several pilots in full-scale systems which have been able to self-seed themselves in a matter of 3 to 6 months. So this perception of really difficult to self-seed a system is not so much the case with PDNA. So just a really high-level summary of the comparison of the two is shown here. But I only really want to make 2 points, which are major distinctions, is that PNA is a side stream process mainly with anaerobic digestate. PDNA is used for mainstream processes typically. And PNA has this heavily engineered environment, and PDNA does not have this heavily engineered environment. But this heavily engineered environment for PNA has created a barrier for New Zealand to use annamox or even consider it because it makes seeding so challenging. And because of this challenge with PNA and starting up PNA, I would argue that we have this presumption in New Zealand that annamox in most forms or any form is really an unachievable process to try and execute. But yet PDNA doesn't require this heavily engineered environment, and because it's been shown to be able to self-seed itself in a well-executed project, we really think it's worth putting back on the table as an option for New Zealand and a viable process for New Zealand to consider using in the future. So when considering the state of PDNA globally, it is an actively pursued technology in the US and the EU and China. It's commonly employed for tea and polishing, as I said, so it's used at plants which already are meeting a high level of nitrogen removal. It's often using fixed film processes because it requires the retention of this biomass, which is quite slow growing, which is the Annamox. So it's usually implemented with technologies like MBBR, IFAS, or deep bed filters. And additionally, currently there's a lot of research and transparent development going on in PDNA, particularly in the US because WRF and the DOE have put a lot of money towards really open and transparent projects and development. So there's a lot to learn in a very open environment. So when we consider the relevance to New Zealand of what PDNA could do, well, New Zealand's getting stricter limits imposed for several plants with these new wastewater standards. Chemicals are quite expensive, like COD and caustic. We don't have endless CapEx budgets to build brand new plants. And if you look to bolt on tertiary systems like nite and denite systems, they typically come with a higher OpEx than starting with greenfield systems. So, and additionally, we have a lot of oxidation ponds, which may need nitrogen removal, and we think PDNA could be an attractive option following ponds if it ends up being a suitable technology. But one of the other things that's potentially different for New Zealand, which is compelling, is that compared to current PDNA practices, we rarely are in a space of nitrogen polishing. So rather than going from a total nitrogen of 5 to a total nitrogen of 3, we're typically going from a total nitrogen of 20 to 10 or 20 to 8 or 5 or no total nitrogen limit to some total nitrogen limit. So, so the potential exists to employ PDNA in applications where we remove significantly more of the nitrogen load, either via post-anoxic denitrification with carbon or what could be PDNA. So whether that's truly an optimal approach from an NPV perspective, we don't really know, but it's still a tool that's probably quite useful and worth understanding more about. And so I've set the scene. So Song, come tell us about the pilot that we did.
Yeah, sounds like a good thing to try out. But there's a Chinese slang which says, in Chinese, 是驴子是马拉出来溜溜. The literary translation is, you can only tell it's a horse or a mule by letting them have a race. So we do the pilot at the Palmy plant. So we have an old MBBR pilot. We have been making it used for different occasions. And for this one, we want to figure out whether it's in fact as good as it sounds in the theory. That we want to understand how robust, how sensitive. And then if we're lucky enough, we can grow some Annamox bacteria, which would be fun, beautiful fun. And the last one, we can do it at the same time. It's mainly for health safety reason. We try a different carbon source, sodium acetate instead of acetic acid. It makes the handling easier. And luckily we did that because we had pipe bursts once. So the first decision we made for the pilot is kind of, where do we put the PDNA? So Louis mentioned about the context in New Zealand. This is a typical one we can see in New Zealand in Palmy plant. So we put it between oxidation ponds and the tertiary clarifier. Oxidation ponds remove most of the BOD beforehand, makes our nitrification easier. And the tertiary clarifier, right now used for chemical phosphorus removal mainly, but it can also remove any biomass coming out from our PDNA plant. So here comes our horse or mule. We don't know. So we have used this pilot plant for MBBR trial to find best design parameters for media, etc. Try different media as well. For this one, we try to use it to realize PDNA. So the first reactor with the aerator beside, it's very hard to, I don't know how to do it. How did it work either? So this is the first aerobic reactor with media and the aerator here. This is a feeding pump feeding into the first reactor, where we expect nitrification happens. By adjusting the flow rate to the first tank, we can control the ratio of nitrate and ammonia coming out from the first reactor. And the second reactor got a mixer and carbon dosing. So by controlling the carbon dosing rate, I can control how much partial denitrification we can do. So let's see the result of the partial denitrification. PDNA, this is the PDN part. So the PDN part, at the beginning, as Louis mentioned, normal operation, we get very little nitrite in our wastewater, 0.2. And then by controlling the carbon dosing, we managed to get a big boost of nitrite and then manage stable for 2 months-ish. And then somehow the influent pump refused to work. So we have to put some temporary solution and try to bring them back. Took me a month to bring them back to operation, and we see the nitrite comes back and looks promising. And then the blower decided to refuse to work. So yeah, in reality, it's much harder than in theory. So we managed to maintain the high nitrite concentration. So that means we do get the PDN part working. And how about the A part? That's the Annamox part. So Annamox monitoring is based on mass balance. So in the anoxic tank, the ammonia is removed in 2 mechanisms. One is the bioassimilation, another one is the Annamox. So we know how much is removed, and we know how much assimilation based on the carbon dosing. We can calculate how much removed by Annamox. So that's the mass formula, which you're not interested. And that's the results. So the green line is how much nitrogen ammonia removed by Annamox. And the result is almost 0. It's not surprising to us because based on the literature, they do say at least 3 months you start getting Annamox activities, self-seeding. And because the disruption in between, we never really run continuously for over 3 months. So we hope we can run it longer so that we can prove, we can get to see more how it goes. On the other hand, we found the carbon source is quite useful. The sodium acetate performs really well to ramp up the surface area removal rate. So we get a similar result to acetic acid we commonly use in the many New Zealand wastewater plant. So, and it's safer, doesn't need any HACCP certification. And when we reduce the carbon dosing, we can see the SAR reduce. That's why when we try to encourage partial denitrification. Okay, come back to the findings. So the partial denitrification is feasible. We can make it with a very simple plant, little automation. And the Annamox growth takes time. I think it's possible, but we just need longer time. And the performance of sodium acetate is robust. I'll pass back to Louis.
We don't have much time, so I'm going to blow through this. Thanks for that. So with that pilot experience, we turn our attention to a full-scale application at the Tokoroa Wastewater Treatment Plant in South Waikato District Council that we're going to kick the tires on in 2026. The Tokoroa Wastewater Treatment Plant is a biofilm plant which uses trickling filters for BOD removal and a fixed media system for nitrification. And it has a 3-stage post-anoxic MBBR using ethanol, which is soon to be commissioned at the end of this year, conventional denitrification. Because there's no pre-denitrification, we're in a position of doing all the denitrification in a post-anoxic system with a nitrate concentration of 30 milligrams per liter. So that means we're going to be dosing a lot of COD and paying a lot for chemical. Well, we're not. Council is. So, and the denite MBBR originally was designed to use methanol as a carbon source, but the carbon source was reassessed and switched midway through the project due to supply chain issues and a few other issues. But using ethanol is really advantageous in this situation. So ethanol as a carbon source results in close to a 50% higher removal rate, SARR, when compared to methanol. And this graph right here you see in a lot of different MBBR texts. And it shows that big boost because of ethanol. So we essentially have all this excess treatment capacity and all this excess media area. So we're thinking, well, we might as well make use of it, right? Rather than just have it in the reactors not doing anything. And so after some brainstorming with Annex Caldenus, who's the system supplier, like 2 more minutes, yeah. Lutra proposed to council that we would convert the first reactor into a PDNA reactor and have R2 and R3 as just conventional denite reactors. And so because of the increased removal rate with ethanol, we're actually not increasing compliance risk at all because we have so much excess treatment capacity due to ethanol. So R2 and R3 are going to do all the original work for denite if we need it, and R1 can be the PDNA reactor. And the way that we're going to implement this is by doing multi-point ethanol dosing. So we'll have a dose point in the first reactor and a dose point in the second reactor where we can create different treatment environments based on the amount of carbon we dose, which produces nitrite, or fully denitrifies. Additionally, the payback should be about 6 months based on the mods that we have to make, which are really just piping and instrumentation. And that doesn't even include reduction in alkalinity or aeration. That's really just ethanol. So it's quite conservative, actually. And so to make this happen, we're going to do COD, or we're going to do nitrate load pacing and do COD to N ratios based on that nitrate load. But we're going to have several different COD to N ratios for each dose point depending on the operational mode. So over time, as we see PDNA activity take off in R1, we can reduce the DO concentration in the upstream nitrification system to bleed more ammonia through, or we have the alternative approach, which we can just pump a wastewater before that system directly into the PDNA reactor and meter the nitrogen that way. So for our conclusions, yeah, we think PDNA has a lot of potential in the New Zealand wastewater industry. And the more return on experience we can get, the better we can find to implement it and use it. PDNA has been shown to be self-seeding globally, so we think it's viable for New Zealand because we have this problem with biosecurity and getting a seed population going. From our relatively rustic pilot, we found that the PDNA, or the PDN option, the PDNA process was generally robust and pretty easy to manage. Obviously, we need a little bit more time and probably better automation and control to get the Annamox part going. But yeah, we look forward to the next year in 2026 and seeing what we can do with a full-scale system with a robust control system. And that's it.
Mike Monahan from Palmerston North. Really good presentation, and it's been really great working with you guys. But one question about the Annamox bacteria is, if it's if it takes 6 months to 12 months to grow a really good seed, what kind of risk does that present to a plant if you should get that colony knocked out by anything?
You want this, or you want me to take this?
Yeah,
okay, I'll take this. There is risk. And I think in most installations and references where it's been implemented as a retrofit, and most of them have been, it's really carefully thought through. So typically what they end up doing is they have to disrupt the upstream process. So if, you might use an ABAC, like ammonia-based aeration control aeration system to really try and get tight control. But the idea is that you're blowing 1.5 milligrams per liter of ammonia out rather than 0.5, right, rather than full nitrification. So not to jump into those details, but yeah, there is risk, but it's typically been managed relatively well. It's typically been executed by relatively large utilities with a lot of internal resources like Hampton Roads Sanitation District in Virginia and DC, areas like that. So there is risk, but it's manageable. They've shown that it's manageable. There was also a study at Noman Coal, which is a Noman Coal wastewater treatment plant in Virginia outside of DC, where they showed that they can actually switch to full denite and then switch back to PDNA without the PDNA being affected. So again, like that seed bacteria, it is quite critical to get that, and I think That's the risk you have to manage. But once that is established, and again, focus a lot on establishing that we think the process of establishing Annamox in a PDNA process is far simpler than a PNA process. Should be a manageable risk. Does that answer your question? Yeah, thanks.
Awesome. Thanks, Tim.